Okay, so with this, my suggestion in the beginning is to draw these out, right? To really like draw them out in Lewis form. So let's do that. So 1.6 F. You can see here you have a group here of two CH2 groups and a subscript 2 tells us how many. You have on the next carbon two methyl groups, right? The subscript 2 tells me that. And then here, remember if it's in parentheses, it's bonded to what's to the left of it. So you got a methyl group on that carbon. Same thing here. The bromine is here. Anytime an atom is in parentheses to the right, that means it's bonded to the atom to the left of it. So let's write this out. So let me see. We have a CH3. We have two CH2s. We have a C. We have CH, 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 and then CH3. All right, so these two are both CH2s based on what's the parentheses and the subscript. This has two CH3s attached to it. And the next one is a CH, CH3. Next carbon is a CH, CH3. And then the next carbon is a C, and we'll put the bromine up top, CH with a bromine. So that's the Lewis form. All right, are you following that? Is that okay?
Okay, so the only question that I have, so the only way the number or the combination in parentheses is going to be bonded if it's only one of them, because I think that's where I was thrown off. So like the first CH2 had two molecules of that, so it wouldn't be bonded to that CH3. It's only if it's one in parentheses.
Yeah, so that means yes, but what that means is that so a CH2, let me back up. So you have a carbon, right? Like this, if it's a CH2, we know that it's bonded to two other things because it's a CH2 and it's got to have 4 bonds to it. So when you have a unit like that in parentheses, what that is two CH, it's like basically a fragment of that chain. So the two CH2s are bonded once to each other, and then the other bonds are satisfied by the two hydrogens, and then them being bonded to what's to the left or to the right of it, if that makes sense. So like if I have a chain like this, let me see if I can concoct something right quick. So I have this. Like that. You following?
Yes, sir.
So that means that in between those CH2s, in between the CH3s, which are on the ends, right? I have 6 CH2s like that. And then the 2 CH3s are here on each end. Like that, if that makes sense. So when you have a CH2, a unit like that, that's really, when you think about the chain itself, it's really just a unit. So it would be like because remember in the skeletal form, every vertex is a CH2. All right, so anytime you see that, then that means that you just have those two carbons bonded to each other. They each have 2 hydrogens, and they each have a bond to the left or to the right, to whatever other atom is there.
So because those CH3s are in parentheses, they don't get their own C in like the backbone. They have to go on the.
Yes, and the reason they don't get their own piece of the backbone is because they already have 3 bonds, right? So let's think about that. If I wrote this out like this, that's a great question. and I added it to the backbone. You following?
Yes, sir.
Now it's got how many bonds to it? It's got 5 bonds to it. So anytime you see a CH3 in the middle of a chain, it's going to be attached to it. It's not going to be a part of the backbone. That's a great question. Did I answer it?
Yes, sir.
All right. All right. Let's see. All right. Is it Reagan? Did I answer your question also?
Yes, sir, you did. Thank
Okay.
you.
Let's go ahead and make that skeletal. This is my backbone. How many carbons is that? Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. There are a lot of ways. Now, this is I'll make it skeletal first, and then I'll explain why we picked that as the backbone. So it's 8 carbons. So that means it's going to be 7 strokes. And you can count that. 1, 2, 3, 4, 5, 6, 7, 8, like that. And then the end carbon here is a CH3. Every terminus, this is what we call a terminus, is a CH3, right? Every vertex is a CH2 unless something else is there, right? So we're going to leave these 2. We'll leave these. When we get to a 4th carbon here, that has 2 methyl groups on it. So we're going to put them on there just like that. CH3. I always like to show the methyl groups. You don't have to. You could just draw a line, and the end of it is understood to be a CH3. And then we have a methyl group here. We're actually going to name this too, since we're here. We open the door. You got a methyl group here. And you have a bromine here. Is that right? So this carbon is right here. This carbon here is here. This carbon is here. This one is here. And then you see the carbon with the 2 methyl groups here. That's the CH2. That's the CH2. And then the CH3 is here. Are we okay with that?
Yes, sir.
All right. How many, remember we talked about these groups the other day. These are what we call methyl. I think I explained that the other day. All right, these are methyl groups. How many of those do we have?
4.
4 of them. Good. That's important because we got to group them all together. Remember, we got the backbone or the parent is the street, and the substituents on the backbone, those are the residents. And on that street, we're going to have house numbers. Everybody's going to live at a certain an address, right? So we're going to start counting from here because the bromine is right next to that terminal carbon. On the other end, right, there's no substituent until you get to carbon 4. So we always count from the end that's closest to the first substituent. Don't worry about that part. We're going to talk about it more. I'm just giving it to you now because it's an appropriate time. So that's 3, 4, 5, 6, 7, 8. All right. Parent is 8 carbons. What is 8? Anybody remember from the skeletal and line structures video? Skeletal.
Like octane.
Octane. Good. So my parent is octane. Excellent. All right. And now I have several methyls. I already named those. And then I have a bromine here. But anytime I put a halogen, group 7, you should remember that from general chemistry, a halogen attached to my chain, normally it would be, we call it bromine. but because it's a substituent, we have to change the ending. So it's bromo. All right. What's the address for bromine? It's at carbon 2, right? Based on our numbering.
I have a question.
Go ahead.
Why is it numbered backwards and not the
Yeah.
other way around?
Oh, no, good question. It's not backwards. Actually, when you have a structure like this, you have to number from the end that's closest to the first substituent. So you see how we got a bromine at number 2, but on the other end, we don't encounter those methyl groups until carbon 4. Like if we count it from this end, this would be 1. Let me change colors. This would be 1, 2, 3, 4. Is that right? If we start a number from that end?
Yes, that's right.
Mhm. So the rule is that you want all your substituents, anything that's on the backbone, to have the lowest number possible. So you always start counting from the end that has the closest substituent to it. So if you look at the 2 ends, the end where the bromine is closer to the end than the other end where the methyl groups are.
Okay, thank you.
All right, so we got a bromine at location 2. So we're gonna write that 2 bromo. You always capitalize the first letter, right? What about those methyl groups? Where are they located? I'm glad you brought this question up, Reagan. This is a load, it's like a pinata. All kind of good stuff in here. So where are my methyls located?
3, 4, and 5.
Okay. How many are on 5?
2.
Okay. So I need to, since both of those are independent, I'm not going to put 3, 4, 5. I'm going to put 3, 4, 5, 5 because there are 2 groups on 5. So I'm going to number that like so. 3, 4, 5, 5. Now, how many? What's the Greek prefix for 4? Anybody?
Is it tetra? Or
Tetra. Good. 3, 4, 5, 5. Tetra. And I'll explain all that in a second. I gotta erase that. Methyl. All right, tetramethyl octane. Let's see if I can squeeze this in here. Okay. Octane is my parent because it's the longest chain. We have a substituent at position 2, which is a bromine. So if you notice, the number always precedes the substituent. So its address is going to precede it. So the place where it lives on the chain, we put that number in front to precede the location or the substituent to tell you where it lives. Right. So the street is octane. The address is the number before the substituent, and the substituent itself is the resident. So 2 bromo. The reason I have to put 3, 4, 5, 5 is because both of those methyl groups are on 5, and I have to account for both of them. All right, so all 4 numbers are listed. If you have 5 methyls, all 5 numbers will be listed. If you have 6, all 6 numbers will be listed. But 3, 4, 5, 5, and then the tetra means that there are 4 methyl groups. Right? So 2 bromo, 3, 4, 5, 5, tetramethyl octane. Any questions about that at all?
Yes, could you re-explain how you went from bromine to bromo?
Sure. So when you're doing nomenclature and naming, sometimes you have to drop the ending of your of the atom or the group and change it. So for halogens, like bromine, chlorine, iodine, they always end in O. So you always end those in O. So if it's bromine, then you change it to bromo. If it's a substituent on a chain. If it's iodine, then you change it to iodo. If it's chlorine, you change it to chloro. Anytime you have a halogen, you have to, the ending is going to change to O. If it's a substituent on a chain, if that makes sense.
Yes, it does. Thank you.
All right. Any other questions before we move back to our previous topic? We left off talking about polar covalent bonds and dipoles. By a show of hands, how many of you watched the dipole video? Let me open up the participants. One hand, 3, 4. Okay, good. 5. Okay. We're about 25%. Okay. All right. Good. All right. So we're going to go back to that topic today. And we've been talking about a lot of stuff, but when we left off, we talked about polar covalent bonds, and I think that's the last thing we talked about. Yeah, polar covalent bonds, and we talked about how electronegativity of the different atoms, how it affects bond polarity, right? So if you have a bond, let me just give an example. Today's the 7th. If you have a bond, let's say between carbon and fluorine, right? The electrons in this bond, remember fluorine has an electronegativity of 4.0, carbon, we're gonna say 2.5, right? The electrons in the bond are always gonna favor a more electronegative atom, right? That ability is called induction. It can be an atom or a functional group, which we're going to start talking about soon. All right, so the ability of an atom or a functional group to polarize a bond, we call that induction. So electronegative atoms have an inductive effect on a bond, right? So if we have something like this, where we have fluorine, we put some lone pairs in. I'm gonna just make this a CH3. Come on, Russell. Right? The electrons are gonna favor the more electronegative atom. So we put an arrow in. I talked about that on, when was that? Friday, about the dipole. We put a dipole arrow in, right? Anytime we have a polarized bond, we can show it by putting in a dipole arrow, right? So the dipole arrow is indicative of the flow of electrons. So that's going to indicate the flow of electrons. So that means that the electrons are going to be concentrated on one end. They're going to be pulled away from the other end. And this really is important because it really dictates reactivity, right? So this carbon becomes partially positive. The fluorine becomes partially negative. So if this reacted with something positive, right, that positive species is going to be more attracted to the negative end of the molecule. If it reacted with something negative, the negative species is going to be attracted to the more positive end of the molecule. We're going to talk more about that later. I don't want to get into too deep in the weeds with that yet because we haven't talked about reactivity yet, right? But with a dipole, this is something that's measurable, right? You can actually take a a solution of fluoromethane, which is what this is, or some solution, and test it with a dipole meter, and it'll give you a definite value, like of how polar a particular compound or substance is. Right. So with that being said, we have non-polar covalent bonds. We talked about that, where the difference in electronegativity is less than 0.5, less than or equal to 0.5. The difference in electronegativity, if it's greater than 0.5, is polar covalent, and then greater than 1 or equal to 1.5 is ionic. So all these different types of bonds that we're going to encounter, they're either going to be non-polar covalent or polar covalent. All right, questions about that? So that dipole is important, because you have, when you talk about dipoles, you have individual dipoles. And then you also have molecular dipoles. Right? This is just, it's just a sum of all dipoles, right? Individual dipoles are just the dipoles for specific bonds. But in a molecule, you can imagine you can have multiple polarized bonds, and you can have an overall dipole, like an overall direction of electron flow. So let's talk about that. Yeah, let's go here. We'll start with this molecule. So which is the most electronegative atom in the compound below? How do we know that? What is that based on? And for the record, all of those are carbons, right? So you got carbon, you got nitrogen, got bromine, and oxygen. So those are my four choices: carbon, nitrogen, bromine, and oxygen. Which is more electronegative?
Nitrogen.
Think about it. So,
Oxygen.
oxygen. So the trend for electronegativity, if you let me refresh you on that. Electronegativity increases. This is for the periodic table. Increases from left to right and from bottom to top. So you have NO, and this is FCl Br. So if you look at bromine, it's actually below nitrogen and oxygen, right? So even though it's further to the right, it's below both of those atoms. Right, so oxygen is actually the most electronegative. So, be consistent. Right, and if you look at the periodic table, you could see that there are a few periodic tables you could probably Google that have the electronegativity values listed. But oxygen is the most electronegative out of all the atoms there. So let's go over here and let's see if we can figure out what types of bonds we're dealing with, right? So can somebody look up the electronegativity of nitrogen, oxygen, and bromine?
Nitrogen is 3.0, oxygen is 3.5, and bromine is 2.8.
All right, so now let's look at the bonds. So the CO bond, let's look at that, because there's a carbon here. And we know carbon is 2.5. So is the carbon oxygen bond polar covalent or non-polar covalent? And which way is the dipole? And how do we determine polar covalent? Right, we need to find the difference in electronegativity. So we just subtract the numbers, right? So for this CO bond right here, it would be what? Wouldn't it be 1?
Yeah.
Is that polar? What's the scale? 0 to what? 0.5 is non-polar covalent, and then from 0.6 to 1.5 is polar, well, 1.4 is polar covalent. So this falls in that range of 0.6 to 1.4, doesn't it? So that CO bond is polar covalent. Which way would the dipole go? That's why I had you look up the electronegativities. The dipole is always going to go where?
Where's the oxygen?
It's going to go, that's exactly right. It's going to go towards the oxygen because oxygen is the more electronegative atom in that bond. So it's going this way. Right? Anybody not following that or not catching that? All right. What about the carbon bromine bond? What's the difference in that? Because there's a carbon here. The difference in electronegativity here is what? Is it 0.3? Bromine is 2.8, carbon is 2.5. Is that right? So is that bond polar covalent or non-polar covalent?
Non-polar covalent.
It's non-polar, good. Now, it is gonna still have a very weak dipole because bromine is a little bit more electronegative than carbon, right? So, and that's important when we think about intermolecular forces, which we're gonna talk about sometime this week, maybe next week, but it will still have a weak dipole towards bromine, even though it's non-polar. Now it's going to have a weak dipole towards bromine, but it's not a polar covalent bond. All right, what about the nitrogen carbon bond right here? We can just I'll just pick this one. And carbon has an electronegativity of 2.5. So the difference in electronegativity there is going to be what? 0.5, is that right? So what's the classification? Is it polar or is it non-polar?
Can it be considered both? I don't think it can, but can it, since
It's got to be one or the other.
0.5?
It's got to be one or the other. So if we go back to our scale, we said that it was greater than or equal to 0.5. Where is it? Here. So greater than or equal to, I'm sorry, less than or equal to 0.5 is non-polar. Greater than 0.5 is polar, and then greater than or equal to 1.5 is ionic. So let's say that that is, for the sake of this discussion, is non-polar. Even though you probably will still have a weak dipole, actually not too weak, a pretty decent dipole towards nitrogen. And again, the scale that's used to measure or determine whether or not a bond is non-polar or polar covalent, it depends on what book you use. Like in some books, it's the non-polar is 0 to 0.3, right? So depending on what scale we use, but we'll stick with this scale. It's not that big of a deal. We can stick with the scale that we're using. All right, let's go to the next question. All right, it says, which of the following statements correctly describes the typical bonding of carbon, nitrogen, and oxygen in organic molecules? So the first statement, it says carbon participates in 4 covalent bonds, oxygen in 2, and nitrogen in 5. How do we know that's wrong? And which of those statements is wrong?
Nitrogen can only participate in 3 and not 5.
Excellent. Nitrogen can only make 3 bonds. It's got 3 bonds and a lone pair, a non-bonding pair. So, right, so that's what we're looking for. So we know carbon makes 4 bonds, oxygen makes 2 bonds, and nitrogen makes 3 bonds. Right, so the correct answer is here. Right. So in organic, when you see carbon, it can be 4 single bonds. We already talked about this. It can be a double bond and 2 single bonds, or it can be a triple bond and a single bond, like that, right? Or in some special cases, it can have 2 double bonds too. In the case of something like an alene. And then nitrogen is here, right? And then oxygen, under normal circumstances, it'll have 2 bonds and 2 lone pairs. But it can also have, I think I showed y'all this already, 1 bond, 3 lone pairs, or it can have 3 bonds, 1 lone pair, and a positive charge. All right. But this is talking in general, like when you see oxygen, in general, is going to have 2 bonds to it. Carbon is going to have 4 bonds to it. Nitrogen is going to have 3 bonds to it. All right, let's go down to here. And I'm gonna cut this out because I want to talk about this in some detail, so we can talk about these molecular dipoles. All right, and we're going to look at each one individually, and then we'll go back and answer the question. Right, so for HCl, we'll write that out. I hate that this paper is all grainy because it looks like the electrons are there when they're not. I got to fix for that though. Let's clean it up some. Right, so that's HCl. And then the other molecule is NBr3. So we'll write that out like that. We know nitrogen has that trigonal geometry, CO2. Like that. And BF3, so F. This is also trigonal. F. All right. Now let's take a look at CO2. Let's talk about that one first. So CO2 is symmetrical. In general, you have a molecule that's symmetrical, it will not have a dipole. So a symmetrical molecule will not have a dipole. All right, let's look at it. So we think about the dipole arrows in the CO bond. Which direction should that arrow be going? Towards oxygen or towards carbon? And how do we know which direction a dipole arrow should go?
It's going towards oxygen because that's the more negative atom,
More electronegative atom, exactly.
and it's doing the same thing on the right.
So now we need to think about these dipoles. So a dipole is actually a vector. It's a vector. We describe it using a vector. So that means it has size or magnitude and direction, right? And so the dipoles are going to be equivalent for the CO bonds. And so one is going one direction and the other one is going the opposite direction. Those dipoles are going to cancel. Because they're going to be vectors of the same magnitude, but they're moving in opposite directions. Right, same magnitude, opposite directions. All right, questions about that? So that will not have a dipole because it's symmetrical. All right. All right, let's look at BF3. Right, what do you think about the dipole between boron and fluorine? Boron is all the way over on the other side of carbon, and then fluorine is the first halogen on the right, and it happens to be the most electronegative atom in the periodic table. So what do you think? What are these dipoles going to look like? Are they going to be towards boron or towards fluorine?
Towards fluorine.
Towards the fluorine. So we got one here, and one here. Right? And again, these are vectors, and so each BF bond has its own individual dipole, but because they're vectors, you can add them up, right? Because they have magnitude, so you can add them, and they also have direction. So in general, the direction of electron flow, we can say is here, right? So this molecule would have what we call a molecular dipole. Right, that's the sum of the vectors, and they're all going in the same general direction. So each bond has an individual dipole, but then the fact that they're all going in a general direction away from boron, we can also say that you have a molecular dipole for this species. All right. Questions about that? What do you think about NBR3? I think you're going to see something similar there. All right, nitrogen is more electronegative than bromine. Is that right? We just said that up top. I think nitrogen is 3.0, bromine is 2.8. Is that right?
Yes.
So all of these dipoles are going to be going this way, like so. And the lone pair also has, it's in an orbital. And that even has a lone pair is in an orbital, and that's going to have a direction as well, right? Anytime you have a lone pair on an atom, I mean, that those are the electrons, and they're not bonded to anything. And so they're going to be away from the atom. What do you think here? You got your individual dipoles, but you also have kind of a general direction of electron flow too, don't you? So you could say that this is going to also have a molecular dipole in that general direction. Questions about that? Any questions? All right, what about HCl? What do you think? That's a fairly easy one to think about. All right, chlorine is more electronegative than hydrogen, so it's going to be polarized in that direction. Right, and anytime you see have a dipole, you also have to, well, you can also think about the fact that for that molecule, part of it is going to have a partial positive charge. If you look at like an electron cloud depiction of a molecule like this, part of that molecule is going to be partially positive and the other part is going to be partially negative. And it's the same for any of these, right? So this is partially positive and this is partially negative. Right, this will be partially negative, partially positive. And the reason for the charges is simple, right? The dipole is telling you where the electrons are. So the end where the electrons are, because electrons have a negative charge, is partially negative. The end where they're leaving from is partially positive. I think we talked about, some of you all in lab yesterday, we talked about the proton and that this is the reason why we call hydrogen, when it's bonded to electronegative atoms or atoms more electronegative than itself, we call it a proton, right? Because it's partially positive. And we can think about it as H plus, right? With no electrons. All right, any questions about that? So that obviously we know the answer to this now is CO2. Will not have a dipole. All right, let's see if we can knock out, never mind, we can go back to here. All right, it says for the elements rubidium, fluorine, and oxygen, rank in order of increasing electronegativity. So that's from least to most. Rubidium is a metal. So anytime that's the case, 99% of the time, rubidium is going to be the least electronegative. Like metals have very low electronegativity. They give away electrons like candy. All right. So, and then we know that the most is fluorine. Is that right? Because we just discussed that fluorine has an electronegativity of 4.0. Right. So rubidium is the least. So it should be first, like it is here. Fluorine is the most. Do we have a combination of these atoms where fluorine is on the far end? as the most electronegative atom?
No.
No. So in this case, the correct answer is not here. It should be rubidium is less electronegative than oxygen, which is less electronegative than fluorine, but it's not there. All right, somebody answer number 5 for me. A polar covalent bond is a bond in which what? One more time.
Is it A?
Greatly different electronegativity, yes. All right. If it's an electrostatic attraction, that's not a bond, right? That's a, well, you've been taught that it's called an ionic bond, but that's really not a bond. It's an attraction, like the attraction between sodium and chlorine, right? Sodium is positive, chlorine is negative. That's an attraction. There's no bonds, there are no shared electrons. So it's just an attraction. All right, it's 10:51 and I gotta stop. So any questions